Okay? Now, we are going to talk about this list of things here, but here are 12 BFFs, and that's a big list. So I don't think you want to memorize all of that. I think you want to memorize what it means to be domain, range, continuity, and all that. And we've begun that conversation already. So let's start in with our functions. The first one is called the identity, and its equation is y equals x. So see where it says the identity function, and then it says y equals? Okay, now we're going to sketch it. If y equals x, then aren't you going to plot 0, 0, 1, 1, 2, 2, are you following along, guys? Did you read it? And then connect all the dots. And the identity function is just your linear function. Every line is a version of that. Obviously, if I change its slope, it becomes steeper. If I change its y-intercept, it moves. But every line is a variation of the identity. Okay? So we have the name, we have the equation, we have the graph. That must be memorized. Now, can we fill in the other things just based on what we know? What is the domain? Negative infinity to infinity. Doesn't this thing go all the way left and right? It also goes all the way up and down, so its range is negative infinity to infinity. Would you say it is continuous? Can I draw the whole thing without with my pencil? Yeah, there's no breaks in it. There'll be breaks in some of these. There's no breaks in there. Would you say this is increasing or decreasing? Left to right, always left to right. Left to right, we are increasing. Symmetry. Now, the symmetries we check for are the x-axis, y-axis, origin, and identity line. Wait a minute, that is the identity line. It is symmetric. It has its own symmetry. Okay? So it does have symmetry to the identity. Does it have symmetry to the y-axis? No, because if I fold my paper where I get this instead, it has to land on itself. What if I folded it this way? Nope. What if I folded it across the origin? Yes. So this one has symmetry about the origin and itself. Is it bounded? In other words, does it have a ceiling? Floor? No, we're not bounded anywhere. Now, extrema. This is a new word for us. Extrema means maximums and minimums. So if I had, this one doesn't have it, so it's kind of hard to discuss it. But if I had something like this, this would be a relative maximum, or sometimes called a local maximum. It is not an absolute maximum, because what does this curve do? Keeps going. So this isn't the highest point on the graph, but it is the highest point in this locality, right here. So what about this? This would be a local minimum or a relative minimum, but not an absolute minimum because points go down further. Can you think of a shape that has an absolute minimum? absolute minimum? A lowest point, period? Sure does. So this would be both a relative, local, and absolute. So when we talk about extrema, we're looking for high points and low points. The line doesn't have any. The line has no asymptotes. Right? However, we have end behavior, and we need to discuss this. When you write end behavior, you will use this notation. We're going to talk about what it means. But that is your end behavior notation. This is calculus notation. And it says, what happens to my function as I go all the way to the right? X approaches infinity, all the way to the right. What happens to your picture? As you go to the right, what are you doing? Going up. Positive infinity. That tells me that as I continue drawing to the right, my pen just keeps getting higher and higher and higher. What happens on the left side? This is the left side. X is approaching negative infinity. What's happening? Going down. We are not going to fill in everything for all of these, but we will the first couple just to see what's going on. Alright, so your end behavior is going to be two statements. They're going to look just like that. It says the limit of the function as we go to the right is positive infinity. That means there really isn't a limit, it just keeps going. Alright, next function. The quadratic or squaring function. This sheet, we've used it for years, but this sheet calls it the squaring function. You can also call it the quadratic function if you want. And it's y equals x squared. And you know what that looks like, right? What does that look like? This? You can plot points if you want, but that's what it looks like. So let's talk about its domain. What's its domain? Oh, negative infinity to infinity. Remember, domain is x's, so look left, look right, how far do you go? If you go forever, then it's negative infinity to infinity. How about its range? Look up and down now. 0 to infinity, and you would write that like this. Continuous? Yeah. If they're not continuous, you will have to stop drawing and start over again. I don't have to stop drawing. I can do that whole thing. Increasing or decreasing? This guy is actually doing both. So you would have to say, yeah, from left to right, always. So you would have to say, from negative infinity to 0, we're decreasing. But then from 0 to infinity, we are increasing. Does that make sense to everyone? Basically, left to right, your pencil going up or down. Starts out going down, then it's going up. That guy have any symmetry? He does, he has one. What symmetry does this guy have? Y-axis. y-axis. Ooh, flashback from yesterday. If I have y-axis symmetry, what kind of function am I? At least some of us will end it up. Even, this is an even function that has y-axis symmetry. Bounded, does it have a ceiling or a floor? It has a floor. So this one you would say bounded below at y equals 0. The floor is at 0. It doesn't go past that. Does it have any high points or low points? No high points, but it has an absolute minimum at the origin and a local minimum at the origin. Local means on that part of the graph, you're the low point. Absolute means on the entire graph, you're the low point. And that point's both. Any asymptotes? No. End behavior. So remember, this is our notation. Every time you do end behavior, this is how you're going to write it. Right? Miss Ludington and Miss White, and Mrs. Ludington, Miss White, now there's sticklers about that. If you don't use the right notation, you're going to lose points. So make sure you have your end behavior set up correctly. And then look at your picture. What happens as I go to the right? What's going on here? Positive infinity. What happens as I go to the left? Also positive infinity. Good? Alright, let's get the rest of these pictures up here. Then we'll come back and talk about whatever other aspects you want, but let's get them older on. The cubing function. Y equals x cubed. Zero, zero, obviously. 1, 1. Negative 1, negative 1. 2, 8. Lordy. Here is your cubing function. It's a squiggly. Continuous? Yep. Does it have any symmetries? Actually, it has one. Origin. It has an origin. Alright. Next, we have the reciprocal function. The reciprocal function is y equals 1 over x. Alright, here's our first discontinuous function. If you look at a fraction like that, can x be 0? So we're going to drop in a nice little vertical asymptote at x equals 0. Because, no matter what, x can't be 0. Now, I want you to think about this. Can y be 0? Think about that. Is there a number that you could put in for x and get 0? No. Shaking our heads, some of us are, some of us look like deer in headlights. Think about it. 1 over something, is that ever going to be 0? Nope. So we have another asymptote at y equals 0. Neither variable can be 0. However, if x is positive, won't y also be positive? So I'm going to have points in quadrant 1 where they're both positive. Where else am I going to have points? In quadrant 3 where they are both negative. So that is a picture of the reciprocal function. Now, let's go through our list. What is the domain of this? What are the x's that are allowed? Negative infinity to 0, and then 0 to infinity. Would you buy that? How about the range? What's the range? Same thing. I heard somebody say it. Good job. Same thing. Everything but 0. Everything but 0. Is that continuous? Absolutely not, because I can draw a piece, then I have to pick my pencil up and draw the other piece. So it is discontinuous at x equals 0. Everything is going great till I get to 0. Then I have to pick my pencil up and draw that. Is it increasing or decreasing? Now be careful, left to right. This piece is clearly decreasing. Hey, check out this piece. It is also decreasing. So it is a decreasing function. The reciprocal is a decreasing function on its domain. Obviously it's broken at 0, but the whole part that you can draw is going down. Does it have any symmetry? It has a lot of symmetry. Well, not a lot. But is it symmetric about the origin?
Yes.
Yeah. How about the identity line? Is it symmetric about that? Yeah. So it has 2 symmetries, the origin and the identity. Ceiling and floor, bounded above or below? Be careful, you're looking at the whole picture, not part of it, the whole picture. Is there a floor? Nope. Nope, nope, nope. There's a floor for this piece of it, but we're looking at the whole picture. There's no floor. And there's no ceiling, not bounded. Does it have a high point and a low point? No. High points and low points, remember, are bottom of valley, top of hill. We do not have that phenomenon in this problem, so there are no extremes. Are there asymptotes?
Yes.
Yes. You have a horizontal at y equals 0, and you have a vertical at x equals 0. End behavior. What happens as I go that way? Positive infinity, that way. What's happening to my picture? The farther out I go, it goes down, and it goes down forever to 0. And so it bottoms out at 0. And I'm going to put a little plus sign there, because when I approach 0, I can approach 0 from the top, or I can approach 0 from the bottom. So when we're describing this, we're gonna say, to the right, we are approaching 0 from the top, positive numbers.
You get marked wrong if you forgot the full sign.
Yeah. And then, going to the left, what's happening to my curve? It's going higher, but not infinitely higher. It's not going to infinity. It's going to 0. But this time, it's coming in from the bottom. So here, we're getting closer to 0, but we're coming in from the top side. Here, we're getting closer to 0, but we're coming in from the bottom. And remember, end behavior is what happens at the ends, left and right. All right, square root function. Y equals square root of x. Anybody remember what that one looks like? Square root function? Starts at the origin, and kind of up and out, like that. Make sure you have that curvature right. It's not this, not that. It's up and out. That's your square root function. What's the domain of the square root function? 0 to infinity. So the domain is 0 to infinity. What about the range? 0 to infinity. This is leveling off, but it continues to go up. It goes up forever. Exponential function, y equals e to the x. E does not stand for exponential. E is Euler's constant. You remember that from last year?
2.7.
Anybody remember what you used E for last year?
It was like a number.
It was
What?
like the
Natural
Log,
logarithms.
yeah.
It's the base of the natural logarithms. When you do ln, that's base E. Okay? So this, what I'm going to draw is an exponential function. They use base E, you could use base anything, and your picture would look like this. That is an exponential function. It goes through point 0, 1, because you know if your exponent is 0, your answer is 1. Anything to the 0 is 1. So it contains that point, comes down closer and closer and closer, and then shoots upward. Does this one have an asymptote? It sure does. It has a horizontal asymptote at y equals 0. This is its horizontal asymptote. Speaking of your natural logarithms, y equals ln x. Looks like that. So this one has a vertical asymptote at x equals 0. Kids sometimes get this one mixed up with the square root function. Remember, the square root function literally starts at the origin and goes out. see why they're kind of similar? But the square root function has a starting point. This guy keeps going forever and ever. Sine and cosine. All right. Did you guys graph these last year? Probably not. We're gonna spend time later doing like real sine and cosine graphs, but for now, I want you to draw a hill and a valley on your paper. Now, technically, they're only supposed to be up one, but I want you to make it bigger than that, otherwise it's gonna get too smashed up in there. But the regular sine curve is gonna go up and down one. But I'm not worried about that right now. I just want you to see a hill and a valley. Now, you don't need to continue it on, but please understand that it does. Okay, it goes on forever and ever. That is your sine curve. Y equals sine x. Don't say sin, that will make you sound silly. Y equals sine x. Cosine is very, very similar. In fact, they are the same curve, except for what? What's different about it?
Starts higher.
Shifted, yeah. So the sine curve goes through the origin. I remember that original sin. So origin sine. The cosine starts at the top. These two are our first example of bounded functions. Alden? Big birthday celebration, fire you out. These are bounded. Why are they bounded? Because they have a 4 and a 0. So these are our first bounded functions. And even though it's not really important at this moment, they are bounded below -1 and above at -2. They have infinitely many extrema. Would you agree with me? Infinitely many. Because you've got hills and valleys forever. Alright, we're almost done. What's next? Absolute value. You know what that one looks like. Absolute value. V. The absolute value function has all of the same characteristics as the square root function, because this is essentially a U with straight lines, right? So it has an absolute minimum, all that same stuff. Greatest integer. All right, this is a little tricky to draw. So here's what I want you to do. I want you to put a nice solid dot at the origin. And I want you to color over one space and put an open circle. And then I want you to step up right above that open circle. That should be the point 1, 1. Put a nice solid dot at 1, 1. And then draw over one space and put another open circle. And then up. Just like that. So all those little steps are one wide and one up. This is the greatest integer function. Sometimes it's written like that, and sometimes it's written like this. On your calculator, it's just INTX. That is the vocabulary on your calculator. This is my least favorite function because it's just a mess. Domain is negative infinity to infinity, but range is only integers. It isn't strictly increasing because while the steps are going up, is this increasing? No, I mean, it's just a tough function. I hate it, so I won't be spending much time on it. And then the last one is the logistic function. The logistic function is another one where we're going to have to spread things out. We have a horizontal asymptote at 0, and then we have another horizontal asymptote at 1. And then we have this funky little curve. Looks like that. So remember the cubing thing we drew earlier? It's like a cubing shape, that squiggly thing, but it's like it's sideways.
It's between
0 and 1, yeah. So on your paper, I'd spread those out because otherwise it's going to be all crunched up in tiny little space. Is that bounded? Yeah, that's another example of a bounded function. You have your work cut out for you because you need to know those shapes well enough that if I said to you, does the logistic function, or is the logistic function increasing or decreasing, you would be able to answer that question. Is the logistic function increasing or decreasing? Increasing. Yeah, increasing. If I said to you, is the absolute value function bounded below, bounded below, but not above? So you need to know the shapes well enough to answer those kind of questions. Are we clear on that?
Yes.
All right, let's answer some questions. Then 1.3, here we go. I've already signed 1, 2.
Yes.
Okay. 1.3, here we go.
What? Yeah. Just finish it.
1.2. None of that stuff is wrong. That was part of the, which was
Are we good?
Yeah, we're good.
Remember, I'm old, I get confused. Y equals the absolute value of x plus 1. Your job is to sketch this. Now, we need to review our rules. We talked a little bit about them the other day. First of all, what shape is this? A V. But the V has been moved. Any number you put into the problem, anywhere you put it, is going to alter the V. All right? What does it do when you put a plus 1 on the x? This is different than this. This is a horizontal shift, and it's not plus 1, it's actually minus 1. So this is going to be a V here.
We have to draw a line so it's bounded, or is it just because of the x-axis?
that's just.
I just mean like, is it ever gonna be above the x-axis?
Oh, yeah.
So then do we have to draw a line around? Or
You
we
just draw
draw
the x-axis and draw, you're gonna draw your x and y-axis, and then wherever your picture is, it is. So this one, I know it's not one of our, on the paper here, but what would this be?
It would be above
Up
on the y.
It would be up, this one would be up one.
Okay.
So, boys and girls, critical, 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 that you see the difference between these two, and you know how to handle them. If the number is hooked to the x, inside the problem, hooked to the x, it's horizontal. And it's the opposite of what it looks like. So, +1 is actually left. If it's outside the problem, just kind of tacked on to the problem, then it's up and down, and it's exactly what it looks like. So this is up 1. Alright, what about the next one? What shape, first of all? Parabola. Where is it?
Right one, or right two.
Right 2. So you're gonna label that point 2, 0, you're gonna draw your little parabola in, and you're done. ln x minus 2,
Natural law.
natural logarithmic function. Even though I've done this for so long, I still like to draw my basic picture, right?
So you always start at 1, 0.
Yeah, it always goes through point 1, 0. It doesn't start there, it goes
It
through.
goes
that.
through, yeah.
Now, what is gonna happen this time now? That's what I'm graphing.
Just,
What's gonna happen?
does it have to go through negative?
Well, just in words, what happens in the picture? It goes down 2. Now, will going down 2 impact my asymptote?
No.
No, so the asymptote's staying the same. But going down 2 means I won't have the point 1, 0. I'll have the point 1, negative 2. And there we go. Tell me about this next one. Negative 1 over x. Which basic function are we using? Reciprocal? So Ben, what's your thought? The normal reciprocal is in quadrants 1 and 3. Let me draw it. Remember this guy? That's your normal reciprocal. A negative out in front turns you upside down. So if we turn that thing upside down, I still have the same asymptote, but now I'm over here and down here. I simply flip it. A negative out in front of your function turns you upside down. Oh my gosh, there's so much to remember.
Oh, shoot.
Good thing you're smart. Pay close attention to where that +1 is.
It's not with that.
It's not with the x, so therefore,
Just go up on the line.
so I'm gonna take my normal square root function, and instead of starting at the origin, it's gonna start up 1.
It's
Alright, so which basic function is this? Cubing. So I know the normal cube squiggles through the origin.
Yeah.
Alright, so what's happened here?
Shift right to 0, 2.
Right
Oh,
to.
right.
So I'm gonna have that exact shape, but it's not gonna squiggle at the origin, it's gonna squiggle at
2, 0.
sin x plus 2. Now remember, original sin. So the normal sign looks like that. One hill, one valley. It keeps going, but that's enough. Starts at the origin, goes up one and down one. That is the normal sign. Now what am I doing to the normal sign? Shifting it where?
Oh,
Let's do it. Let's do it. What was that?
I don't know what that was.
What was that?
Something else. I don't even want to think about it.
Wait, what do you think it was?
Oh no, they're not back, are they? Remember we had the whole blood.
We did?
Oh, yeah. Last year. Hopefully they're not back. Alright, so I'm gonna take this whole thing and shift it up 2. So now it's starting at 0, 2,
Yeah.
and it's gonna go up to 3. Right?
Yes.
And down to where? 1?
Yeah.
So it looks like that. Alright, you try next 2. You try the last 2. See what you can do with, all kinds of transformations.
Start at acid to negative.
So for the first one, I went ahead and do my exponential up here. And you don't have to look back. You just made one. You don't have all these memorized yet. But there's my exponential. And I'm going to drop it down 1. So remember, there's an asymptote at 0. I'm dropping that down to -1 now. There's an intercept at 0, 1. That's now going to be at 0, 0. And there we go. And what did you do with that guy? Did you get him done? What's it look like?
Down.
The downward speed.
Normal V, but it is going down because a negative out in front turns us upside down. Let's stay focused. I don't know how you can be unfocused and all this fun and now me. Alright, here we go. Part 2. Identify which of the 12 functions is odd. So there are 4 of the 12 that are odd. look at your pictures. What does odd mean again? Odd means you have symmetry about the origin, right? Okay, so that means what you see in quadrant 1 is mimicked in 3 and so on. So, then if you do anything that's odd, what's D? You know, our basic functions, our basic 12.
That would be,
Look at your
Reciprocal.
reciprocal, all right, I'll go with that. Reciprocal is odd.
cubic function,
Cubing function is odd.
identity.
Identity is odd. You're on a roll.
I don't know.
There's one more.
Sin.
Sign. Sign is.
Sign.
Sign
He makes it.
Sign is odd. So before. Okay.
That makes more sense.
All you just woke up long enough to ask the question, how can sign be odd? So let's look at that first piece. If I took these, each of those points, and threw them, I print on a like, what do you call it? That thing that shoots. If I had one of those, it would take all these points and just shoot them into the All right, number 20. The 6 functions that are always increasing. The 6 functions that are always increasing.
Linear.
Linear,
What, Jim?
Exponential?
No.
they're linear,
The cubing.
cubing, linear and cubing.
Absolute.
No.
Square root function.
Square root function,
You're gonna say exponential.
exponential function.
Good, Pete.
So sine is not, because what is sine doing?
I never said identity.
It's going up and
The
down.
cosine?
Cosine's also going up and down. Increasing
natural-
means it only goes up.
The natural
The
logarithm.
natural logarithm function.
Logarithm, yep,
What's that?
The natural logarithm function.
yep. As it goes up,
We need one more.
I don't know the other one.
Absolute value.
no, absolute value.
Square? Logistic?
Yes, where?
There's only 5.
Logistic, come on.
Logistic.
What's not going up?
You are gonna have to be careful. LOG cannot be your abbreviation because you have logarithms and logistic. So make sure you're writing enough of the word to know. So they are linear, cubing, square root, exponential, logarithmic, and logistic. Those are your functions. All right, 21, this is fun. The 3 functions that are decreasing from negative infinity to 0. So on this part of the picture, they're going down. 3 functions that are doing that. Exponential increases that are coming.
Oh.
Absolute value,
But I thought you were.
absolute value comes down until it gets to 0.
Cubic function.
Parabola?
Squaring or quadratic, reciprocal, yep, there they are. Reciprocal, absolute value, and squaring, all are coming down on the left-hand side of the picture.
Uh-huh.
All right, couple more. 3 functions with infinitely many local extrema. So, tons of highs and lows.
Wait, absolute
So
value.
there's no.
Wait, which one's the sine?
Squaring is quadratic.
Sine and cosine.
How is that?
Right?
How is that what? Eli, when I draw the squaring function, which way is my pencil going? Right?
Sine and cosine.
Sine and cosine, number 22, sine and cosine. Because all they do is go up and down. The other one is a tricky one, it's the greatest integer. The greatest integer has infinitely many maxes and mins because on this interval, you have a max, then you have a different one on this interval, and this one, and this one, and this one. I hate that function.
Me too.
The three functions with no zeros. What are zeros? X intercepts.
Y equals
So three functions that don't touch the x-axis. Logistic is one. Reciprocal is one. Exponential is the other one. Very good. Reciprocal and exponential. Never touch the x-axis. Three functions whose range is all real numbers. So in other words, you go all the way down and all the way up with no breaks. Continuous all the way up and all the way down. Identity, that's linear. Identity and linear are the same
Cubing
thing.
function.
Cubing, oh no, logistic doesn't go all the way down.
Come on, Brent. We need one more.
Natural water.
Logarithm, yep,
Which one?
natural logarithm. Goes all the way down and all the way up. Last one. The four functions that do not have this end behavior. Now, what does that mean? That means they don't shoot up to infinity. So, does your parabola shoot up to infinity? Yes. Your view shoots up to infinity. What are some functions that don't do
Greatest
that?
integer.
Sine and cosine, definitely. No, greatest integer, just keeps marching.
Logistic.
Logistic,
So we're full of dogs.
How you say that?
there's one more that doesn't reciprocal. See it. The reciprocal doesn't go up to infinity, it comes down to zero. All right, my friends,
Good day.
we'll do more of this tomorrow. All right, we'll do more, wait,
Yeah, we don't.
We don't do.
We see you next week. Monday.
Monday.
Because we didn't have class, there's school Monday.
can you say I hate this schedule?
I really don't.
We had you 3 days in a row.
Well, I wanna have you 40.
My brain says.
Our ears are sensitive.
In the good old days.